Welcome to the fourth in our 2008 summer lecture series, sponsored by the Communications Department. That's the plug. Today we'll be hearing from Roger Falcone about what it takes to make molecular movies that are so fast that they can show the details of chemical reactions and how materials transform during phase changes right down there at virtually the molecular level. After graduating from Jamaica High School in Queens, which is where he grew up, Dr. Falcone majored in physics at Princeton University and then got his PhD from Stanford in 1979. His scientific career was set when he was at Princeton, and he heard a visiting lecturer from Bell Labs talking about ultrafast lasers, and that struck him as something that was really nifty and something he would like to do, and he's been doing it for a few years now. He joined UC Berkeley's physics department in 1983. He eventually became its chair for 5 years. Meanwhile, he was becoming involved with Berkeley Lab and the ALS, where with Robert Schoenlein, he designed and eventually built the ultrafast X-ray facility at Beamline 6, which just started up last year, I believe, or maybe the year before that. He became director of the Advanced Light Source in 2006. He also directs UC's Multi-Campus Institute for Materials Dynamics under Extreme Conditions. He's a fellow of the American Physical Society, the Optical Society of America, and the American Association for the Advancement of Science. And when he's not devising ways to make ever shorter pulses of lasers or coherent X-rays, Dr. Falcone has long been active in science education, including a stint as president of the Lafayette School Board and the co-directorship of UC Berkeley's participation in California Teach, which is a statewide program aimed at producing 1,000 new science and math teachers every year for the California schools. It's my pleasure to introduce Roger Falcone.
Thanks, Paul. What I thought I would do today is give you a sense of what goes on at the Advanced Light Source, which is the big domed building sitting at the top of the hill. I'm not sure if everyone who's visiting here for the summer will get a tour of the place, but if you're interested in a tour, you should come see me. If you're an undergraduate, you're interested in working at the ALS, you should contact me. We have lots of opportunities for students. We have lots of students involved in our work. Fiat Lux is the Berkeley motto. Let there be light. So I always think it's applicable to the Advanced Light Source. So the Advanced Light Source sits here up on the hill overlooking the bay. We're well connected to the environment here, which is both the Berkeley campus and our colleagues across the bay at Stanford and the Stanford Linear Accelerator Center, where they also do work with light sources. What we have here is a machine that produces extremely bright beams of X-rays. So if you imagine this laser pointer as sending out a beam of red light, what we do is we produce beams of X-ray light that are perhaps 1,000,000 times more powerful than the X-rays that are used in your doctor's office, either a dentist or a doctor that might look at a broken bone. So these are extremely powerful beams of X-rays for science, all sorts. We do imaging, so I'll show some of our favorite images ranging from the Earth to a protein molecule here that's showing little dots of atoms. We do everything in between. So the science that drives us, we have recently begun to think about it as going into dimensions and times and energy spaces that are at the level that is appropriate to what we might call grand challenge science. So this is science that is needed to solve the energy issues, climate change, modern materials, all sorts of frontier science. Grand challenge science requires moving along an axis in energy space, moving along an axis in time space, and moving along axes in real space. And what that means is looking at objects down at the nanoscale, or looking at single atoms. So going to the extremes of the space dimension. Going in the time domain to ultra-fast processes, which are measured in attoseconds. Attoseconds are time scales associated with the orbit time, the Bohr orbit time of an electron going around a proton in an atom. It's about the fastest we can think of when we think of constituent atoms. The fastest kinds of processes are at that attosecond time scale. And finally, in the energy domain, we think of going below 1,000th of an electron volt in energy. So these are energy scales that are associated with the low-lying excitations of collective systems. So in all those domains, the science we're doing at the light source is pushing the frontiers there. So what does our machine look like? Well, this is a cartoon of what's called a storage ring X-ray source. It is what the advanced light source is, and the advanced light source is the premier soft X-ray facility in the country. And I'll explain what soft X-rays are in a second. But essentially, the machine, top down, kind of looks like the size of a football field. There is an accelerator that accelerates electrons. There is a booster ring here where the electrons circulate around and around and around, going faster and faster. They're accelerated until they're moving at relativistic energies, 99.999% of the speed of light. For those of you, it has energies measured in billion electron volts. The electrons are then injected into another ring where they go around for about 8 hours. Some of them are lost. They collide with each other and they're kind of scattered away. But they circulate for about 8 hours. And when electrons go around a ring like this, and electrons are made to either curve in the space they're going or wiggle through some magnets that are placed close, they radiate X-rays. All light comes, in fact, from electron motion, whether it's jumping energy states in an atom or electrons that are made to wiggle through magnetic or electric fields. Light comes from wiggling electrons, and in our case, the electrons are made to wiggle in a series of devices we call insertion devices that are placed in this ring, which is called a storage ring because the electrons are stored there. And when they're made to wiggle, beams of X-rays come out tangent to the curve here. So each of these tangent lines here carries a beam of X-rays to a different experiment. That is the advanced light source. About 2,000 users each year come to the advanced light source from all over the world, scientists who want to do some special type of science, and we set them up with an experiment at the end of one of these lines. 2,000 of them, sometimes they come for a week or a month or a day. Sometimes they don't even show up. They do their experiments remotely over the web by controlling some instruments. Or sometimes they're here and they set up shop and they're here for the whole year. But we provide beams of X-rays to scientists who have really good science to do. That's our job. So how does that work? Well, we take a bunch of electrons that's in that storage ring, and they're moving along at nearly the speed of light in a direction that is indicated by this arrow. We then have magnets that are perpendicular to their motion, north-south fields, that make the electron wiggle. So for example, if there's an electron heading right toward you and I have a magnet that is up like this, the electron wiggles like that. And when it wiggles, the electric field lines that come from that electron wiggle, and that's light. Electric fields that are varying in time. And a machine that makes them do that is pictured here, and a beam of synchrotron radiation comes off here. The light actually comes out like a beam of light because the electrons are moving relativistically, and the opening angle of the light is less like a flashlight and more like a laser beam. It's really collimated. The machine that, one of the newest machines we put in is a machine that looks like this. It's, about 6 by 6 feet. It costs about $1 million, and it's a lot of precision stainless steel. And inside of it, it's really kind of gorgeous. It's very precisely machined magnets and materials. This one was made over in Japan. It's called an undulator or a wiggler because it makes the electrons wiggle and produces these beams of X-rays. And it's those beams of X-rays, of course, that we want. This is sort of a technical slide that just gives you a sense of the intensity of the light versus the energy of the photons, or the wavelengths of the photons. And we produce light that not so much radiation at low energy, not so much radiation at high photon energy. This is long wavelengths, that's short wavelengths. But in the middle, which are the soft X-rays, we produce more light than any other facility. And that's why people come here, because they want these X-rays that are not extremely penetrating, but interact with matter in interesting ways. And so our machine has a certain peak in its spectrum, just like the visible light from the sun has a peak in its spectrum at green light, right? That's where our eyes are most sensitive from the sunlight. This spectrum is at photon energies much, much higher than you can see. It's in the extreme ultraviolet or soft X-rays. Now, this is one other so I have two technical slides. This is taken off a website from the Center for X-ray Optics here at Lawrence Berkeley Lab. And you don't have to worry about the numbers so much, but it tells you how deep X-rays go into matter as they get to shorter and shorter wavelengths. So very hard X-rays up here at 1 angstrom type of light go through maybe a 10 to the 4 microns of material, maybe a centimeter of material. And so X-rays that are at 1 angstrom can go through your teeth or go through your finger so you can see a broken bone. But X-rays that are in that, what I'm calling softer energy, where the ALS, remember where it had its peak here, tend to not go into matter very much. It might go in a micron or so. Your hair is about 100 microns thick, so actually the X-rays don't go in very deeply. That's good news. It means we can't look deeply into things, but we can use our light to interact very, very strongly with material, and that's good because that tells us a lot about the material. It means this is water, this is plastic. How far does the X-rays go through water or plastic? And that's important because a lot of our materials that we look at are in biology. And so there's a lot of water and there's a lot of carbon and hydrogen in those materials. And we can go through maybe a few microns of material, and that's about the size of a cell. So that allows us to look inside cells. So this is a top-down view of the machine, that circular storage ring here, and all those lines that come out tangential to the ring where all the X-ray beams come out. And at the end of each of these beams are different experiments, each of which is specialized for a different type of science, whether it's biology or physics or chemistry or environmental science or all the other things. I'm going to run through a few examples of the science that we do to give you some idea of what goes on in this ring. So there are about 40 different instruments here that serve these 2,000 scientists each year. One of the interesting new experiments that we put at the end of a beamline is run by a professor from UCSF and a scientist here at LBL, Carolyn Larabelle, and she has something called the National Center for X-ray Tomography, which is jointly supported by the National Institutes of Health and the Department of Energy. And that means that it's both important science and important work that might have some clinical application to real medical physics. So there's an example here of an image of a cell that she produced. So this is a cell. You can see the nucleus. You can see some other organelles. And we do these pictures of it called tomography, which it's like a CAT scan of your body, where you can look inside the cell, rotate it around, take a look, color code for different organelles, different pieces of the cell, different colors. We can elementally understand what elements are there and what objects are in there. Another experiment, this is the instrument she uses, which has some lenses, some X-ray lenses. A specimen sits here. What they do is they take an individual cell, stick it in something like a straw, and hold it in water and rotate it around and take pictures of it. So what is this? This is a picture that she took with this device of a single cell. This is a yeast cell. It's budding yeast, budding because it's splitting, right, from 1 into 2. Okay, this is the same yeast that is used to make beer, I'm told. And you can see the nucleus in the center, different organelles that are all color-coded because we can tell what is which. So this is like taking an MRI of your body or a CT scan of your body, but this is done at the microscopic level, looking inside the cell, seeing things like the roughness of the surfaces and identifying the elements and the objects that are inside the cell. So there's one example of the kind of work we can do. And lots of scientists want to come and look at different objects not just budding yeast cells, but all sorts of things. Another thing we can do is take X-rays that are slightly higher energy and look at things like bones, except we don't just look at bones macroscopically, we might look at their substructure. So this is looking at different bones, the substructure of 30-year-olds or 60-year-olds, seeing osteoporosis in the bones. Okay, again, the resolution is much, much better than a millimeter here. It allows us to look at the microscopic structure. So see, these are two examples of sort of microscopic and maybe what's called mesoscopic examination of biological samples. Again, our X-rays are needed to see inside them and to chemically identify what's going on. This is an experiment where we look at trace metals in the ground. The idea is that in old mines, for example, in California, remember we had a gold rush and we had silver rushes. A lot of environmental damage was done by essentially taking those materials out of the ground and chemically separating and leaving all the crud behind. Very toxic environments now, we have to understand how those toxic environments are dealing with life and other chemical processes that are going to go on in the local environments, let's say of a pool of water that was left at a mine. So here we take small particles that are measured in millimeters. So this is about a millimeter-ish size little rock. We can tune the X-rays to examine what the chemical constituents are in that material. So here's something where you look at manganese. You make that light up, or you make the iron light up, or the zinc light up, or the nickel light up, because what we do is we tune the X-rays in our beams, and that makes each element light up so we can find out where the elements are in small materials. We generally call this spectral microscopy. Spectro because we tune the X-rays to make different elements light up, and microscopy because we're looking at small things. And that's essentially what we do with the ALS, is spectral microscopy. But this work is very important to environmental remediation. And again, the people who are doing this work don't necessarily understand our machine, but they're doing great science, and we provide the photons and the techniques to allow us to look inside. Another material that's a little more physics-oriented is called graphene. You know that carbon comes in very different forms. Carbon comes in the form of diamonds, which are very hard and clear, and an insulator, and very expensive. Carbon also comes in the form of graphite, which is inexpensive, soft, opaque, cheap, right? Pencil lead, graphite. Same diamond, just how things are arranged. Well, one form that carbon comes in is graphene, which are sheets of carbon where the atoms are the little purple things here are bound together in rings with other carbon atoms in layers, kind of like mica rock, and you can peel them off, layers of graphene. And that's why when you write with a pencil, leave a little bit of graphite behind. That's the pencil mark. Okay. Well, we just take a little bit of double sticky tape, lay it on something like a pencil, pull off one layer of the graphite, which is a graphene layer, and it turns out this is a very, very interesting material from the perspective of physics and potential devices. And so we're studying the electronic properties of single layers of graphite called graphene, finding out that if we apply a little bit of electric voltage to it, we open up what's called a band gap, which can turn on or off conduction in the material. So we have a molecular switch at essentially just a few atom level. Eventually, this might lead to a new type of tiny, tiny transistor that's going to be part of microprocessors, say 10, 20 years from now. So the physics that we're doing here to understand the basic material is important, but also the potential device applications is super important, because eventually this might make microprocessors that are maybe 100 times faster or maybe 100 times smaller than the ones we have now. But what's critical is our ability to probe this material with X-rays to understand its electronic structure, which has never been measured before. Another thing we do for energy research is to shine X-rays on material and look at the X-rays that come out. Sometimes we shine X-rays on material and electrons come out, and we study those. Sometimes we just look at how the X-rays get scattered or we make an image from the illumination of the X-rays on the material, but sometimes we look at the photons that come out that change energy. We put a certain wavelength of X-rays in and something else comes out. And understanding what the something else that comes out tells us all about how the materials that we shine them on are behaving. And so here we're looking at nanoparticles suspended in a liquid. We understand how these clusters are working in either gas or liquid phase environments. The idea here is this is helping us to understand new types of photoconverter, photovoltaic types of conversion. Shine light on a material, understand how it can generate electricity. That sort of photovoltaic work, understanding the basic behavior of the materials that might be useful for that kind of photovoltaic conversion is key. Another thing we do is to study combustion chemistry. We do this with Sandia Lab, which is in Livermore, California. And what people do here is they take a burner, a combustion burner, and it's like a Bunsen burner, and they light it, burn a fuel, and then probe with X-rays as the flame moves from the bottom to the top of the burner. And what that tells them is the time history of the combustion process. Because early on it's down at the bottom, later on it's up at the top. Understanding the combustion is critical, and shining X-rays on the material helps them to understand the combustion process. Why is this important? Well, we all know that there's energy efficiency is very important. How we utilize fuels is critical. There may be 1,000 or 10,000 chemicals in a common gasoline fuel. When it burns, you produce thousands more chemicals, all in the intense chemical reactions that are going on. And it isn't just simple combustion, chemical reactions. The flame itself is very turbulent, and the mixing that goes on, the turbulence that's involved, totally drives the chemistry as well. So it's a very, very complex environment, and it turns out that shining our X-rays on the material is a way to understand it. So just to give you some sense of the things they study, down here at the bottom is meant to be the bottom of the flame, where there's a bunch of fuels that are going in. So there's CO, there's hydrogen, there's CO2, there's water, and so we see that at the bottom of the flame. As you go up, these hydrocarbons begin to form into more complex materials, and then eventually the hydrocarbons all agglomerate into soot. And so if you've ever put a glass on the top of a candle flame, you'll know that it soots, and you can get some coating of the soot material. We go all the way from the basic fuels to the soot. That soot is important because it creates particulates that are bad for us to breathe and so on. But understanding all of these chemical processes here is done. We can identify very, very complex organic materials because of the slight shifts in the X-ray absorption of different hydrocarbons. And so we have a very, very good chemical specificity on all of the thousands of chemicals that are produced in the flame. Another thing we do is to take pictures of objects without any lenses. And this is just a fundamentally fascinating idea. Pretty much all of you know that a lens can form an image of an object, right? If I have a microscope and I have a specimen at the focal plane of the objective, you know that the objective of the lens collects the light that comes off the object and focuses it together with my eye on the back of my eyeball. And so there's a real image, just like in your first year physics labs where you had a lens and you had maybe an object and an image plane in the lens maker formula. Let's say you didn't have a lens. Let's say you couldn't make a lens. And in the X-ray region of the spectrum, we can't make lenses that are good enough to see really, really tiny objects or to see objects at all. Let's say you take away the lens. So you have something that looks like a microscope. You have a beam of light, which in our case is X-rays, that illuminates an object. Normally, you'd have a lens here that would form an image of that object in the microscope. But let's say you took the lens away. All of the light that would have been collected by the lens is still there. And we know exactly how lenses behave. They bend light. Okay? We know the physics laws of the bending of light. Why can't we just take the scattered light, put it onto a detector like a television camera without a lens here, without an image, and do a mathematical algorithm to compute what the object should look like? Do all the bending of light not in real space with a lens, but by computer algorithms. That's called lensless imaging, diffractive imaging. It takes the speckle pattern of the scattered light that has all sorts of angular and wavefront distortions on it and does a mathematical transform, a Fourier transform of that light, and creates an image of it. So this is called lensless imaging. It's a phenomenal idea. If I scatter light off an object, let's see. So you see if I put the beam of light right on the screen here, you see a dot. But let's say I bounce it off the table. Do you see the object there? It's a scattering pattern. Okay, it's a little bit kind of interesting. It's got some diffuseness to it and so on. Okay, if I put a lens right here, I would get an image of the table, right? The microscopic roughness of the table. But let's say I don't do that. Let's say I just take that light there with all its intensity variations and I put it into a computer, I can analyze it. I can make an image of this table right here, and that's called this lensless imaging. So it's a modern way of making pictures down at the nanoscale that we think is going to revolutionize the way that images are made without lenses. Another way we make images to try to look at really, really tiny things is we shine X-rays on a material, and Einstein told us that one of the things that happens when you shine light on a material is that electrons come out, the photoelectric effect. Well, let's say we don't look at the light that comes out, but we look at the electrons that come out of the material. We can collect those electrons and form an image, just like an electron microscope forms an image of an object. But in an electron microscope, electrons illuminate an object, you collect the electrons, and you make an image, just like you would with photons of light. Here we combine the best of both worlds. We shine light on a material, but we collect the electrons. That allows us to make an image which has a sensitivity connected with the tunability of the X-rays. In other words, we can make each element in the object light up. We can make sometimes the zinc light up or sometimes the calcium light up. But we get a spatial resolution determined by the electrons, not the wavelength of the light. So you might know that your ability to see how tiny an object is limited by the wavelength of the light. It's a fundamental law of physics. But here we're not limited by the wavelength of the light. We're limited by what's called the de Broglie wavelength of the electrons, which is much, much tinier. So X-rays in, electrons out. We put it essentially the back end of an electron microscope on here, and we can look at all sorts of tiny samples, whether they're magnetic samples. We can look at proteins. We can look at elementally selective things in a new type of microscope that's an extremely popular instrument for us. For example, we can see whether the material is magnetic. Here we did an experiment where we had a sample that we bombarded. It was a piece of carbon, and we bombarded it with protons. And it turned out we made it magnetic. Now, normally you don't think of carbon as being a magnetic material, right? You think like iron or manganese or nickel or cobalt or things like that that are magnetic, but not carbon. But we were able to light up the carbon in the sample, light up the iron in the sample, light up the nickel and the cobalt, and we found that all of the magnetism in the sample was actually due to the carbon. Okay, fascinating way to create a new type of magnetic material. We could only see this with the microscope under this what's called the photoemission electron microscope, or PEEM. We also work a lot with industry. This is a project we do called with the Center for X-ray Optics called the EUV lithography project. This is the way that we're going to make make microchips, say in 5 or 10 years, using very, very short wavelength light to print transistors on microprocessors. The Center for X-ray Optics has been involved with an international consortium of chip makers who are interested in how are we going to make microchips in a number of years. They get faster and faster each year, but the chip makers have to invest $1 billion or $2 billion to make a chip plant. They have to get the answer right. They have to know how they want to build chips in 5 or 10 years to do it right. And so this is part of a consortium that is looking at a new way of making microchips. Intel is involved, the government is involved, and a lot of researchers here at the laboratory. And it turns out our X-rays are particularly good for understanding and developing the technology to make these microprocessors in the future. And this will keep us on what is referred to as Moore's Law, which is the ever-increasing growth in the density of microchips, the doubling each year of the number of doubling every 18 months of the number of microchips on a microprocessor. This technology is going to be key to that. So it's another type of imaging that we do with the light source. So where are we? We're up here in this dome. Here's the cafeteria down here. I guess we're down here. We have a nice little environment up here where we work. We're building a new guest house, and this is a good thing for all our users. We're building a hotel on LBL site, and in a few years you'll be able to come and stay here. And Berkeley campus will probably run it as a hotel, so you can come and stay in the lab. And let's see, the cafeteria here and the guest house here and the ALS here, you never have to go home. That's our idea here. Everything you need. No cars, it's fine. So I advertised this talk as molecular movies, but everything I've told you about is pretty static, right? We're looking at samples, and they're not moving. They're not dynamic in any way. Well, I'm going to tell you now a little bit about making molecular movies. How do things move around? This was a series of pictures taken, 130 some odd years ago, a bet between these two people at Stanford about whether a horse that's running, whether all four hooves leave the ground at any time when the horses are running. And so this is one of the first fast motion movies trying to solve a physics question. Does the horse ever have all 4 feet off the ground at a time? And there was a bet. And it's hard to tell just by watching the horse. But if you take a series of fast movies, you can tell about the motion. And in fact, in one of the frames, you can see that all 4 hooves are off the ground. We're not looking at horses anymore. Okay? We want to look at atoms and how they move around in chemical reactions. So what's the deal there? Well, one, to see a horse, you can have visible light. To see atoms, you need X-rays. So 4 orders of magnitude decrease in the wavelength of the light. To see a horse move, you need pictures that are maybe 1/10 of a second or 1,000th of a second, millisecond, kind of a shutter speed on a camera. To see atoms move, we have to have a camera that's 13 orders of magnitude faster. We have to be able to measure in femtoseconds or attoseconds or picoseconds. Okay, so we have to use X-rays. We have to do it a lot faster. So how do we do that? Well, one of the things is we've got to pick a science experiment. What do we care about? Well, one of the first experiments we did was to take a solid, and here's a solid. The granulation is all the atoms in the system. Okay? If I have a solid like this piece of wood and I hit it, just like that, I send a sound wave into it and I compress it. And so this is a computer simulation of what happens if I hit the surface here, either with a laser beam or mechanically. It sends a shock wave into the material. Each of the atomic planes moves. And so there are theories about how all this works. But this is a simple kind of dynamic situation to set up. Can we see the atoms move in a system like this? Well, here's a more complicated version of this. Here's a supercomputer simulation of that same thing I just showed you schematically. Okay? We have a block of atoms, and again, the granularity are individual atoms. This is iron, and the gray is BCC, a certain atomic structure of iron in a material. But if I push on the side very hard, sort of equivalent to shooting a bullet on it, okay? What happens is the material transforms into HCP, hexagonal closed pack, rather than body-centered cubic structure. The atoms just kind of torque around, kind of like diamond graphite, just changes in the positions of the atoms. Okay? What's left behind is a bunch of yellow stuff, which is defects in the system, okay, that are left behind because you don't transform at all. There's a nice little blue region in here that's compressed BCC before it relaxes into HCP. Supercomputer took a long time to make the simulation. This is a test of whether scientists understand anything. We can make supercomputer pictures on the computer all day. Question is, does this reflect reality at all? We now have the ability to watch this process to see if our capability of simulation is as good as we think it is by this kind of computer simulation. Another type of simulation people do is if you send a lot of energy onto a surface, it'll explode outward. It'll ablate. Okay? It's like shining a hot amount of energy onto a surface. It kind of evaporates. And this is a computer simulation of the ablation of a surface of copper atoms when we suddenly heat the surface up, if it's a free surface ready to expand. These are the atoms. Some of the atoms come off as blobs like this, but again, the scale of this is only measured in nanometers. Okay? Some of the atoms come off as ions, which are, you can't really see in this light, but there's some glowing atoms here that are ions that come off. Again, our ability to simulate this is, we think is good, but we don't know. So we've got to be able to watch this happen. And so we have these simulations. We're going to use our X-ray pulses to essentially be a strobe light for the atoms. Okay? So you know about strobe lights. You know that they can illuminate a dancer walking across a stage or dancing, okay, a flash of light. So here, we're going to use our X-rays to watch the individual atoms move. And we've done this a little bit. Oh, so this is important in things like plasma physics. It may be important to fusion energy, for example, how atoms move under high pressure, high temperature conditions. But I won't go into that. So what we've done so far is we've scattered our synchrotron light off a sample that we ping. We do that too with a laser. And what we see is the X-rays drop down and bounce around. That shows you this sound wave moving through the sample. And the matchup of this with theory is important to us because it tells us that our ability to simulate is as good as our ability to measurement, and we actually understand the microscopic physics. We also look at when we put enough energy in the material to actually cause it to melt. And we look at the phase transition of the solid to the liquid when we put enough energy in the surface that we make it melt. You all know about melting, taking ice and making it into water as it melts on a surface. Well, we do that very quickly, and we try to understand how that melting process happens. It turns out we can even make a melting process where we don't ever heat it up. We just slice all the bonds of everything holding the atoms together. So if you imagine an ice crystal, okay, if you slice the bonds, remove them with shining light on it, the atoms will just wander away from each other. And so we can see what is in essence cold melting of materials because we individually slice each bond. It turns out that water and ice are fascinating things to watch, and we watch them with our X-rays. Water is a very dynamic system. Water is a series of H2O molecules that are joined together like a small cluster of people at a party. They form together, then they break up, and they reform somewhere else, and they reform somewhere else every few picoseconds. And we can watch those processes happening, again, with the X-rays. So I've told you a little bit about of some of the biology that we do. Sometimes some of our users win a Nobel Prize, and in 2006, Roger Kornberg won a Nobel Prize for his work both here and at Stanford for understanding the structure of a particular protein that was important. So what we are doing in this work is, and I'm going to link this to the dynamics, what we want to do is understand the workhorse of biology, which are protein molecules, and how they behave, their structure, and how dynamically they behave. So here's some sort of protein type molecule associated with biological function. Hemoglobin in your blood is one you're probably familiar with. Hemoglobin might look something like this, maybe 1 million atoms in its structure. The whole job of hemoglobin is somewhere in the center here is something like a catcher's mitt. Okay? When it's chemically triggered, the catcher mitt opens up, grabs onto oxygen molecule, closes up, carries it to some other part of your body, as again chemically triggered, opens up and releases the oxygen. So it's a ferry for oxygen molecules. It looks huge on the scale of maybe the oxygen molecule, which is just a point in the center here, but it's a big molecular machine that's doing its work. Drugs work in the same way. So understanding the structure of biological materials like this, so we understand how drugs can function and how we might be able to design them better, is a big deal for us. So understanding protein structure is very important. The way we do it now is we take the protein molecules and we put them in a crystal form. We make a crystal out of them. So some of you have probably sometimes tried to make a crystal out of sugar or salt, right? You take a saturated solution, put a string in and pull it out and hope that little crystals form, which is an ordered pattern of salt or sugar molecules. Well, here we do the same thing with a complex molecule. We make an ordered pattern of it. We shine our X-rays on it, and it produces a scattering pattern that we can mathematically analyze to understand where every atom is in here. It's called macromolecular crystallography. Okay, and it's a standard thing we do. It's what this fellow won the Nobel Prize for. It's kind of a workhorse technique at our facility. And this is what the pattern looks like. Okay, a series of scattered dots that when you mathematically analyze it, gives you another series of dots, but it's where the atoms really are. Trust me. So the pattern is interesting, but let's say we cause a chemical change in that protein. We open up the catcher's mitt. Okay? Some of the atoms move around a little bit. Okay? And the pattern suddenly changes. The pattern actually doesn't move, but the intensity of the dots changes. And this is showing you how much each of the dots changes. So the green dots changed 10 times. The purple dots changed 10 times, but they got less intense. Okay? So how those dots change is reflective of that small piece of the protein molecule changing. And so this is a microstructure. These are carbon, nitrogen, and oxygen atoms all in a protein. And they look a little blurry because the resolution isn't really that great here. But it's looking right in the center of that protein molecule, something that actually looks like hemoglobin but isn't. Okay, and there's where the oxygen sits. That's the catcher's mitt that's holding on to oxygen. And what we're going to do is we're going to release the oxygen. It's actually not oxygen here, it's CO, but that's a subtlety. You know that CO can be absorbed just like oxygen. Okay, so there it is a few picoseconds later, okay, where the material has been released. So we can look inside these protein molecules and we can image their dynamic function. Okay, watch them catch things and release. Now this is simple in some sense. It's important to us, otherwise we wouldn't breathe. Okay, we're kind of dead, but in more complex things, where drugs are being designed here, what you might try to do is redesign the drug to make it work a little better. We don't muck with hemoglobin because we think it works pretty well. Biology has fixed it for us, but when you're designing a drug, you might want to change the balls and sticks a little bit to make it more efficacious. So, understand the structure of proteins like this, patterns like this if you can make a crystal. But what if you can't make a crystal? And 90% of the time you can't make a crystal. Okay, what's the deal? Well, you do exactly what I did here with the lens, with the lensless imaging, create a scattering pattern that looks for the pointer bouncing off the table looks like that pattern. But if I bounce X-rays off this, I get this really squirrely looking image. Okay? But again, I can computer analyze all of this to get that again. If I can crystallize it, I can get this pattern and do it. If I can't crystallize it, I can get this pattern and get the structure. The problem is that you need a lot of X-rays to do this. You need more X-rays than we even have now. And so we're building a machine down at Stanford that will produce X-rays that are about 1 million times more intense than the ones we produce here. It's called the LCLs, X-ray free electron laser, and it takes a 3-kilometer long accelerator to make it work, to make a beam of X-rays that's powerful enough to produce enough light to hit the molecule and make a picture of a single protein molecule. The problem is when the X-rays hit it, the intensity has to be so high that it blows it up. So that's a problem, but we have lots of protein molecules, so we drop a new one in, take its picture, blow it up. So it's a destructive imaging technique, okay? But that's okay. Takes a few femtoseconds for it to blow up. There's so much light, it heats it up so much, it's destructive. It'd be like taking your picture with the bright enough light that it sort of blinds your eye. That's bad enough. This one totally blows up the object, okay? But that's okay. You drop a new one in, take its picture. But the problem is you have to put enough light in that it blows up really fast. Too fast. So you say, well, I'll put the light in faster and more intense. Well, then it blows up faster. But eventually you win, because Newton taught us that inertia holds atoms around. They can't instantaneously move. Okay? You apply a force, it takes a little time to accelerate. So we think we can make the pulses fast enough to actually do this destructive imaging. It'll revolutionize the understanding of protein crystals if this works, but it's an incredibly high-risk experiment. But the government's putting $500 million into the machine, so we got to do something with it. So why do we care about things that are so fast? I'll just sort of summarize here and say why we care. Nature uses speed. I mean, we're not, we think of life as a dynamic process. I mean, most of us are, we're sitting here fairly stagnant. Many ways, there's not a lot of motion going on, but life is incredibly dynamic. And if it wasn't dynamic, we'd all be cold and dead in the dark, okay? But nature, it turns out, is really fast, and science of technology has to move into fast timescales. So ultra-fast timescales are used in nature to direct energy and information flow, whether it's a computer or a photosynthetic system or an energy system. So for example, in vision, very fast chemical processes happen in a conformational change of rhodopsin, which is the receptor for light in your eye. If nature didn't very quickly react to a photon of light coming in onto a single molecule in your eyeball, it would destroy that material, because the equivalent of a visible light photon being absorbed in a molecule is a temperature rise to about 10,000 degrees. So unless nature figures out a way to react very quickly and conformationally change the structure of the molecule, all the rhodopsin in your eye would just boil away very quickly. But it dissipates the energy by going to conformational change. It changes the heat energy into potential energy very, very quickly. And it has to happen on femtosecond timescales. Another way that nature uses fast processes is DNA. So you go out in the sun and your DNA gets illuminated by ultraviolet light. It would destroy the DNA. But your DNA has a very fast way of reacting to dissipate the energy into lots and lots of thermal modes of the system. So it's a very complex molecule. It can take that one photon of light, which would heat up a local environment to the equivalent of 10,000 degrees, but dissipate it in a whole lot of energy modes very quickly before it does its damage. So nature has this interesting way of using very fast processes. For us, we want to create new materials. We want to make better photovoltaics, for example. We have to understand these fast timescales. So it's critical that we understand these timescales if we're going to improve upon nature in a lot of ways. So final slides. How are we going to do this? We're going to build a new machine at Berkeley. So this is Berkeley. There's the ALS. This is a hill, right, just down there. We want to build a big tunnel underneath it, okay, underneath the hill. Build a new machine, maybe $1 billion type machine. I'm leaving in about 2 hours to go to Washington to convince them this is a really good idea. Okay, we're going to build a tunnel. We're going to put an accelerator in that's going to produce X-ray beams that are even more powerful than the machine we're building down at Stanford. Okay. It'll have an electron injector, an electron accelerator, and then a series of things to make the electrons wiggle to produce X-ray beams coming out the end here. The difference with this machine compared to the ALS is that the pulses are thousands of times faster, and they have a much higher coherency. They're much, much more like a laser for doing that imaging. So the machine looks like this schematically. It's got a superconducting linear accelerator and a bunch of undulators. It's a highly complex technical object that we're going to bury underground for good reason, because it can produce a lot of radiation, and we want it safe under the ground. I'm going to skip the technical things of all of the cute tricks that we're going to do it, but what we can produce is we can produce light that has extremely short pulses, just fast enough to be able to resolve those electrons that are going around in the fundamental Bohr orbits of atoms, the fastest kinds of reactions we can think. Now, this is a very interesting confluence of, it's what scientists do these days when they want to build machines. They come up with a very compelling science case that this is what internationally scientists need. And so we've had workshops with hundreds and hundreds of scientists that have come and said, yep, this is what we need next, because we can't do the work we want to do. And then we say, well, we have a solution for it. And this is the technical solution for it, and it's great. But the next step is to convince you, taxpayers, and the Congress and the President to fund it. Okay, so our big deal here is really to say that this is what the science needs. It's important for the nation to do it, and building that case will probably take us about 10 years to finish. So it's a long time scale, but it's just in time for you getting your PhDs, I guess. So you can come and use our machine. And we have some reasons why our machine, which is the pink band here, is much better than everything else going around in the world. We, of course, have to explain that. I'm going to skip this, what the scientific challenges are. Well, I'll jump to the scientific challenge. So very complex materials have very complex dynamics in terms of the way information and energy flows through molecules. When photons come in a photosynthetic system, it's not quite clear how the energy all flows. This new machine will allow us to watch how the information and the energy flows in a photosynthetic system. There's a very interesting type of nonlinear interaction of light with matter that this machine will be able to do that no other machine can do, and we think that's really the key to driving the science. So it's pushing us into a new regime of technology, but also of science. So here we are in 2008. We hope to have that new machine built, maybe 8 years from now, done, welcoming all of you to a real new world of ultrafast X-ray science. So thanks very much.
I think we've got time for a couple of questions. Wait until we get a microphone to you. Or if, okay, hang on.
Earlier in the lecture, you were showing us the X-ray's ability to penetrate various materials based upon their energy. I noticed there was a dip in the middle of the graph. What is that from?
So each atom has a particular energy level structure, which has to do with the way the electrons are attached to the nucleus. And that leads to characteristic features of both absorption of X-rays and emission of X-rays that is determined by the chemical and atomic structure of the atom. So that dip was characteristic of carbon, or the next dip is characteristic of nitrogen. So each atom has its own characteristic super absorption place, and it's really by looking at those particular dips that we're able to say that's the carbon, that's the nitrogen, and so on. Actually, it gets better than that in the sense that you can also identify the chemical nature of it. So if it's chromium, let's say, in a mine deposit, you can see whether it's chromium 2+ or 3+ or what its valence is as well. So it's very, very sensitive to its chemical environment too.
Can you also distinguish covalent compounds?
Yeah. Yeah.
Do we have another question? Hang on.
Thank you, and good luck on your
Thanks.
trip. Can you say anything more about the implications for cellular communication? So, for example, cells in the body communicating with each other, you're going to be a liver cell, I'm going to be a kidney cell, that kind of thing.
How cells communicate. I don't really have a good answer on it. I could say that we clearly can have an ability to look at chemical signatures that may be triggered in local environments, because we can look at the progression of chemical triggers in systems. We can also trigger them, say with a laser or a heat pulse or an electrical pulse or so on, and we can trigger something and then watch how signals get communicated there. Again, the spectral microscopy says we can look at what's there, what its valence is, what its chemical environment is, and what its time history is. So, rough answer.
I have another question up here, and I'll just do it right now.
So many of the people in the audience are new researchers or teachers doing science, and for their benefit, I would like to ask you what inspired you to choose this area when you were, say you were a secondary level student? And secondarily, how did you get to be able to develop such clear communication by analogy from the atomic scale to the macro scale in which we live? Two questions: your inspiration and to your communication technique, physical insight.
Right, tough. I don't know. Best experiment I ever did was in junior high school. I think it's been downhill since then. But I remember taking a magnet and a salt solution and putting electricity into it and seeing that it all swirled. And I don't know why I did that, but I think I had some experiment with fish that died, and I knew I didn't want to do biology. And so I got more into the physics of it. And then I read a Tom Clancy novel where actually it turned out that this is the way Russians were propelling submarines. Anyway, somehow that was my best experiment ever. And that definitely got me into physics. But as Paul mentioned earlier, I went to a great talk when I was an undergraduate on lasers and ultrafast phenomena by a guy who was at Bell Labs who's now at UC Irvine. Very early on, people realized that you could use light to stroboscopically probe dynamics of matter. And after that, I left the physics department and went into engineering because he was an engineer, and I said that was better. But I came back to physics. The communication part is really part and parcel of what all scientists have to do now. There's no entitlements anymore. Maybe there never were. I'm sure there never were. And so being able to explain to people who fund us, which is the American people through their Congress and through their president, you end up constantly having to have that elevator speech, have the ability to translate whatever you're doing into something that makes a difference in people's lives. And I think we all end up having to do that. There's a course that the Lawrence Hall of Science teaches every spring that I'm involved with called Communicating Science. And it's a wonderful course that takes our undergraduates, teaches them how to communicate to a science audience like this, puts them in the schools, so we partner with our local junior high school. But whether somebody becomes a scientist or a high school teacher or whatever, taking courses that actually focus on communicating science seems to me to be a worthwhile investment. And I think a lot of schools have those now, and they're definitely worth it, just to get you a little bit of self-reflective moment, a little bit of a self-reflective moment on how you do talk to people, critical in that. So I enjoy those courses.
I think what you forgot to say, Roger, was that your dad took you to see backstage Mr. Wizard when you were 10 years old, so that might have given you some inspiration.
Right. Mr. Wizard was the science program on at 7 a.m. in the morning when I was growing up.
The best communicator ever. Right? Well, thank you very much. If anybody else has any questions, you can come on down.
I'll be here for a bit. Thanks a lot.
Thanks.